So here we go with part 4 of section 5.5. We're going to take a look at using substitution on definite integrals. So we're going to talk about how we change variables on those definite integrals. And here's the theorem that lays it out for us. And basically it starts out the same as what we've been doing. It says if you can do a substitution where u is a g of x and it's a continuous derivative closed interval and f is continuous, then we can take what we saw before, that is f of g of x times g prime, and rewrite that as f of u. But because this is a definite integral, the limits of integration change. What used to be a is now g of a, and what used to be b is now g of b. The reason this happens is the original limits of integration were based on the variable being the variable x, but we changed the variable from x to u. And if we change the variable, then those limits, these were x values right here, need to be turned into u values. And so these are going to be u values. And the way that we turn x's into u's, the way we turn x values into u's, is we perform substitution. We take the old x value and we put it into the g of x, the u statement that we were using. All right, we'll do an example, and it should make a little more sense when you see it happen. All right, so here's our problem. We're supposed to evaluate this integral. I have the integral, the definite integral with a lower limit of 0 and upper limit of 1 of a composite function x squared plus 1 cubed. Right? So I think I'm going to use substitution because I do see it being multiplied by something else, and I think I'm seeing the u and the du here, so I'll do my scratch work. U is x squared plus 1. Then the differential du would be 2x dx. Looking at my integrand, I don't have the 2, so I'll call this 1/2 du is equal to x dx. Now it looks like everything should be all hunky-dory. We should be able to do our substitutions. So now we get the integral of u cubed times 1/2 d. I perform my substitutions. I have not yet dealt with the limits of integration. Right? All right, the old lower limit of integration was 0, but if I take that 0 and plug it into my u statement over here for x, I get that the new variable for u is going to be a 1. And where did that come from? I took the 0, plugged it in for x right here. 0 squared is 0, 0 plus 1 is 1. I'm going to find my new upper limit by taking the old upper limit again and plugging it in for x, and I'm going to get then that that new upper limit is 2, meaning that the definite integral from 0 to 1 of x times x squared plus 1 cubed dx has the same value. It's not the same integral, but has the same value as the integral from 1 to 2 of u cubed times 1/2 du. Now, I've done everything that I need to do to perform this integration, so I'll go ahead and do that. The 1/2 is a coefficient, so it's just going to drag along. That's that 1/2 right there. And then when I integrate u cubed, I get 1/4 u to the 4th, and this whole thing needs to be evaluated from 1 to 2. Okay? And so when I do that evaluation, I'm going to get 1/8 times 2 to the 4th minus 1 to the 4th. Okay? 2 to the 4th is what? 16 minus 1, 15. So I get 15/8. And so I'm done. Now, the question that I often get asked is, what about that step where we back substituted, where we took x's and took u's and turned them back into x's? Well, when we did this step right here, when we did the step where we changed our limits of integration, that allowed us to never have to do back substitution. Okay? Now, there are some books and some people out there who will make the following argument. that every definite integral should be turned into an indefinite integral. Substitution should occur on the indefinite integral. Back substitution should occur on that indefinite integral. And then the original limits of integration should be used to evaluate that back substitution. That is not the most common way to do these, nor is it the preferred way to do these, because it adds 2 extra steps to a problem that's already hard enough. Okay? So you will most likely see substitution done this way. Now, if you are one of those people who feels that this doesn't work for them and you just want to do every single problem as a indefinite integral, back substitute at the end to get back to the variable x, and then evaluate using the original limits of integration, I will tell you that that will work. It will just add extra steps and extra time to every problem that you do. Okay? All right, so let's walk through this one again. Original problem, we recognize that this is substitution. So I know it's going to work. So I figured out my u and my du just like I've been doing with all the indefinite integrals. I substituted my integrand using my u's and my du's. The difference is now where did these numbers come from? Where did this lower limit of integration at 1 come from? Well, it was the old lower limit plugged into the substitution statement. The 2, same thing. It was the old upper limit plugged into the substitution statement. So I plug it into that statement and I see what it changes x into a value of u. And then I use those new substitutions. From this step to this step, I just performed integration. The 1/2 was a coefficient of drag. U cubed became 1/4 u to the 4th. Limits of integration show up over there. Okay? From here to here is just evaluating a definite integral, evaluating a definite integral. Okay? All right, let's try it again. Hey, this one looks familiar. I know what to do with this. This is the one where we had to say u was 2x plus 1, then the differential du was 2dx, and then we said 1/2 du was dx to get the substitution to work. So then this became the integral of u to the 1/2 times 1/2 du. Okay? But what about the limits of integration? What's that 0 going to turn into? Well, when I take that 0 and plug it in over there, 2 times 0 is 0 plus 1 is 1. So my new lower limit of integration is 1. My new upper limit of integration, I'm going to take that 4, I'm going to take that 4, and I'm going to plug it in over here and see what happens. Right? 4 times 2 is 8 plus 1 is 9, square root in, 9, right? And now I have the limits of integration are 1 to 9. Right? Now that I've got my limits of integration, this is just a calculus problem. So this 1/2 is just a coefficient, so it just drags along. U to the 1/2, let's see, that's going to become u to the 3/2 with a 2/3 out in front of it. And then this needs to be evaluated from 1 to 9. Okay, so I'm going to get 1/3 times the quantity, 9 to the 3/2 minus 1 to the 3/2. Okay, 1/3. 9 to the 3/2, the 2 is a square root, so square root of 9 is 3. 3 cubed is 27. Minus 1, 26, so I get 26/3. So the value of my definite integral is 26/3. So I'm thinking that these are actually, in my opinion, easier. The definite integral ones are easier than the indefinite ones because there's no back substitution. There's just substitute, evaluate, substitute, evaluate, substitute, evaluate. All right, the integral from 1 to 2 of the quantity dx divided, that's ugly. I'm going to rewrite this. That looks better. This looks a lot like the last problem we did because we have a composite part, but we have no other part that is being multiplied by, but our composite part is linear, so it's the right kind of composition, so I think it's going to work. We'll say that u is 3 less 5x, so then the differential du is going to be negative 5 dx, considering that I only have this over here, I'm going to make this modification. Negative 1/5 du is dx, and now I'll perform my substitutions. This becomes the integral of u to the negative 2 times negative 1/5 du. I need to get my new limits of integration. 1 as a lower limit of integration into that substitution problem is going to give me a negative 2 for my new lower limit of integration. 2 into that substitution for my new upper limit of integration. 5 times 2, 10. 3 minus 10, negative 7. So I get a new upper limit of integration of negative 7. And now I should be able to just do everything. Let's see, the negative 1/5 is a coefficient, so it's going to drag along. The integral of u to the negative 1/2 is going to be a negative 1 times u to the negative 1, all evaluated from negative 2 to negative 7. Okay. 1/5 times negative 7 to the negative 1 minus negative 2 to the negative 1. Remember, it's the upper limit minus the lower limit. So let's see, that's going to be 1/5 times negative 1/7 plus 1/2. Let's see, negative 1/7 plus 1/2 is 6/14, 3/7. Wait, I might need to actually write that one out. That's not making sense in my head. Ah, that's right, Brian. Common denominators. Negative 2/14 plus 7/14. There we go. So 5/14. So 1/14? When it's all said and done. That is the ugliest 1/14 I've ever written. It's not much better, but it is right. 1/14. That's calculus for you right there. The hardest part of it was trying to figure out how to add two fractions together. I can do integration all day long, but add two fractions, woof. All right. So what's my job? My job is to do integration. I'm doing harder and harder and harder problems that are integration problems. We're in the section where the problems are integration that requires substitution. Right? So I'm learning how to do all these substitution problems. Now, this is a really challenging one because I don't see composition anywhere. So I don't know what to do. But I think I see something. I remember this. Do you remember this? The natural log of x is 1 over x. And I kind of see that hiding in there. So I'm going to rewrite this integral. Not substitution, just rewriting it. And I think I see everything I need to see now to make this work. I'm going to call this, even though it's not composition, I'm going to call that u. And then the differential du is 1 over x dx. So then when I do my substitution, this just becomes u du. My new lower limit of integration needs to be this 1 put into that substitution statement. And what's the natural log of 1? Natural log of 1 is 0. And then my new upper limit of integration needs to be e put into that substitution statement. And what's the natural log of e? Well, the natural log of e is 1. And then I'll integrate. Let's see. 1/2 u squared evaluated from 0 to 1. And I get 1/2. And so the value of my integral is 1/2. Well, that wasn't too bad. I kind of liked it. It's a tricky substitution problem because substitution The rules for substitution say look for the composite function, but there's no composite function there. All right? So just be careful with those. All right, that brings us to the end, as you can see, of section 5.5, the end of substitution. And now it's time to move on to section 5.6. All right, have a good one.